Alright, so we understand where the signal comes from and where it travels. But if we're dealing with microvolts, which are super small volts, how does the signal become big enough to see on our screen? That's where amplifiers, gain, and sensitivity come in. Potentials from the brain are not evenly distributed on the scalp, whereas electrical interference usually affects all scalp electrodes equally. Digital systems are basically the same as analog systems as far as their parts, except for the electrode selector panel is in the computer, and there is the addition of an analog to digital converter. Differential amplifiers are designed to measure and record the differences in voltage between two inputs. Remember, two different signals that are compared as G1 and G2 are called a derivation. As time passes, these differences are plotted and connected by lines, giving us waves. The purpose of differential amplifiers are to amplify the difference between two voltages, in our case, two electrodes, and to eliminate unwanted electrical potentials that don't come from the desired location. And we can do that with common mode rejection. The common mode rejection ratio, if you recall, takes out the signals that are alike from both inputs. The goal of differential EEG is to get the difference in voltage between two locations over time. As an example, any voltage that is read at C3 that is similar to the voltage read at M2 will not be amplified but rejected. There are tons of different potential signals coming from the skin, muscles, and the environment. In polysomnography, our amplifiers have a common mode rejection ratio of 10,000 to 1. That means that for every 10,000 common voltage signals, only one gets amplified. In the same way, two different voltages from two different electrodes causes waves that we want to see. Unequal impedance of the electrodes may cause equal voltages to appear differently, meaning the waves will not appear as they truly are. So if your impedance at C3 is 1.5 kiloohms and the impedance at M2 is 20.5, the common voltages caused by the electrical interference will look different. The signal at C3 will come through, and the signal at M2 will be a lot weaker because of the resistance, impedance. This false difference in the voltage will be amplified. The best signal you can put in with scrubbing and electrode placement techniques, the better the signal will come through the PSG without having to tinker with filters or anything. Remember the saying, junk in equals junk out. If you have a poor signal going in, it's going to look bad no matter what you do until you go in and fix it. Here is my crummy example of common mode rejection ratio. We've got all these similar waves coming in off two different inputs. These could be something of skin, or the person's own muscle activity, sweat, or other outside environmental signals like static electricity. There are charges going off everywhere all the time, but they're not always big enough that we see or feel them. If you look closely enough, the exploring electrode has one signal that looks different than all the rest. It's this fancy little cosmic line. That's what we want to find and to get out of both of these electrodes. Because the big mess of monocolored waves are similar in both inputs, all those waves that are not that astrological looking thing, the common mode rejection feature of the filter cancels out these signals and leaves the signals that are different. So once all the similar and non-similar voltages go through the amplifier with the common mode rejection, it should leave the fancy galaxy looking wave that was unique out of all the other signals. Let's talk sensitivity. I'm a very sensitive person. Sensitivity affects how much the pin deflects, making the waves either bigger or smaller. Remember the voltage sensitivity pill? The thing to remember about it is the relationship of changing the sensitivity. The sensitivity value sets how much voltage is required to make the pin deflect 1 millimeter. That means it takes the input voltage and makes it bigger or smaller depending on what you have for the setting. The sensitivity setting does not change the actual amplitude of the wave, only how it appears on your screen, meaning the output. Increasing the sensitivity means you want to decrease the voltage required to move the pin further, making the wave size bigger. So remember that decreasing the input voltage per millimeter makes the waves bigger, and decreasing the input voltage per millimeter makes the waves smaller. Sensitivity affects the output only. So what we're looking at on the computer, not what goes through the system. Check this out. This is an example of what different sensitivity values look like in a time constant calibration signal. The first figure shows that 20 microvolts, it takes 20 microvolts to move the pin 1 millimeter, and it really doesn't move very much. The next figure shows that it takes 10 microvolts to move 1 millimeter, making the wave a little bit bigger, maybe twice as big as the first one. We move on to 7 and 5 and finally 3 microvolts, and by decreasing the voltage input per millimeter, we have bigger pin deflections and bigger waves. Only the amplitude or voltage is changing, not the rise time or the fall time. That, remember, is from frequency filters. Gain is a different setting than sensitivity. It compares the input voltage to the output voltage. Remember, sensitivity deals with the output. We're just changing how it looks. But because the input voltage didn't change, the pin deflection did. So, gain will increase the incoming signal before the amplifiers get to it. And the sensitivity takes that input, processes it to make the pin deflection. You can, quote unquote, increase the signal size by using both, but they are both, they accomplish the same thing in different ways. Both gain and sensitivity affect the amplitude of the wave, again, in different ways. Gain changes the amplitude of the input prior to the amplifier. Sensitivity is after amplifier processing and changes the output signal by lowering the amount of voltage that it takes to make the pin go further. You could say that gain compares the input voltage to the output voltage, and sensitivity compares the output voltage to millimeters via pin deflection. These are common sensitivity settings. The EEG and EOG are both usually a 7 microvolt per millimeter sensitivity. EMG uses 5 microvolts and EKG is 20 microvolts. Respiratory channels use 5 microvolts. G1 and G2 are our typical two inputs, G1 being exploring and G2 being referential. The two input terminals together make a derivation. More than two derivations make up a montage. Remember that EEG signals on the screen are upside down. An upwards deflection is a negative and a downwards deflection is a positive. An example would be an input of 50 microvolts. Subtracting a negative 25 microvolts would equal 75 microvolts. A good thing to know about it would be if G1 is more positive than G2, the pin moves downward because the sum will end up being positive. This is a wiring schematic of how the input signal is collected from the EEG and processed through an amplifier. The top line represents G1, the exploring electrode. The middle line represents ground, where there's no potential at all. And the bottom line represents G2, or the reference lead. A negative signal, upward deflection, at input 1 and no signal from input 2, which would be negative 20 minus 0 equals negative 20, results in an upward deflection. In this example, we have no signal for input 1 and a positive signal from input 2, a downward deflection. 0 minus 20 is negative 20, so the final output is an upward or negative pin deflection. Here we have two signals of equal size but opposite polarity, and they occur at the same time. This causes a pin deflection that is twice the size of that caused by each potential alone. The math goes like this. Negative 50 minus 50 equals negative 100 microvolts. Because it is a negative wave, the output deflects the pin upwards. Here's an example with two signals of equal amplitude and the same polarity. When those signals are processed, for instance, 50 minus negative 50 equals 0. That is the common mode rejection. Two signals of the same frequency or voltage, that's what that is. Here's one that has two waves. G1 has a negative wave and G2 also has a negative wave, but is approximately half the size of G1. When we subtract negative 50 from negative 25, we get an output voltage of negative 25. It's an upward deflection that is about half the size of G1. So that's all for gain, sensitivity, and deflection polarity. I hope this gives you a little bit of a better understanding of how these things are interrelated and how we get the signal from human to the machine. Knowing this kind of stuff makes you a much more potent troubleshooter and more likely to just really succeed in life. How about that?